Hi, my name is Manish Gupta, and in this video number 207, I'm going to talk about the segment anything to model, also called as the SAM model. Okay, so let's first see what can segment anything to model do. So, well, it's basically useful for video segmentation, interactive video segmentation, as you can see in these videos. So let's start with this first one. The user basically just selects some of those objects that they want to track, and on some frame, if the model is not able to track correctly, they can actually provide this interactive signal saying that, hey, the other shoe is not what they were expecting to be tracked or highlighted, segmented by this model, right? So let me play this again. So the user first says, I want to track these two objects, but hey, somehow the model screws up. So then the user can give an interactive input in a particular frame saying, hey, don't track the other shoe. Okay. Now, of course, it could be useful for tracking multiple objects across videos. So for example, here the user has selected 4 of those, and then the model nicely tracks them across the video. Again, here the user is basically suggesting in one frame that these 4 things should be tracked, and in the video, those 4 things are really nicely tracked by the model as segments in the video. And then the last one, of course, the very interesting one where the user has actually marked 3 different balls, and then the model is basically nicely tracking the motion of these 3 balls across the video. So what is SAM2? Well, SAM2 is basically a model so as to essentially take a video and then come up with masklets, as it is called. So for example, here is one of those masklet which is shown. It's basically a combination of masks over time which tries to highlight the cat. Okay. So the input is not just the video, but it's also interactive input by the user. So for example, the user here has specified the big box, as a prompt or as an input to say what they want to be tracked. In some other frames, they can also specify prompts or inputs in the form of points. So the user can actually say that, yes, this is a positive green point, saying I do want to track the cat. And then the negative red points outside saying that, hey, the background is not what I want to track, right? And then the user can actually also specify the input or prompt in the form of a mask itself. So of course, this is very expensive for the user to specify. So therefore, it is basically an interactive video segmentation model, right? Which basically tries to track objects of interest for the user, any object that can be bounded in terms of drawing a boundary in that senses across time. Okay. So basically in this paper, they contribute 3 things: the task, the novel definition of the task itself, the model itself. So they basically come up with the SAM2 model, which basically just does this interactive video segmentation. And then they also come up with data. Okay. So as to be able to train this model nicely. Okay. Since it is SAM2, of course, there was the segment anything 1 as well. And that segment anything 1 was about promptable segmentation images. But SAM2 is about promptable visual segmentation in images and videos. Right? Now, of course, handling videos is very complicated. And videos basically involve, motion. There could be deformation of objects. There could be occlusion of objects, lighting changes, and other factors which make it challenging. There is, of course, other things as well, like camera motion, blur, lower resolution, which can cause lower quality in terms of videos and therefore make it more challenging. So, when we say promptable visual segmentation, what are the prompts here? Prompts are basically things provided by the user's input. So, for example, it could be positive or negative clicks, basically these red or blue points, red or green points. Bounding boxes like the box here in the first frame, or it could be masks like the one that is shown in this frame, right? So from a model perspective, the model basically takes one frame at a time, one frame of the image at a time. It basically, and also it takes the user prompts. So it takes this user prompt, does a prompt encoding, takes a frame from the video, does the image encoding, and then it also retains a memory in a memory bank. So it also has a memory bank. It basically keeps a track of where was this object and what were the features of that object in the past few frames, right? And when it gets this current frame, it basically applies co-attention, cross-attention. Basically, it applies cross-attention with respect to the memory from the memory bank, and therefore comes up with a revised image encoding, which it basically passed to the mask decoder. Mask decoder, of course, outputs a valid object mask for this frame, because that's what segmentation is all about, computing a valid mask for this particular frame, right? And for every frame in the video. Okay. Now, of course, to be able to come up with a very large data set, they follow this paradigm, an iterative way of doing it. So where they start with some initial data, they train a model on that initial data, and then the model is used to annotate a few things. This annotation is judged by actual humans, and that gives you more data to train the model, and the model training happens in an iterative fashion. Overall, they contribute SAV data, segment anything video data set, which basically has like 642.6 thousand masklets. So remember, these are the number of masklets or some sort of object tracked over temporal videos, right? And 35.5 million masks if you look at it, each of those frames specifically, with 50 across 51K videos, approximately 51K videos. Okay. So as that, now how is SAM2 trained? So SAM2 is trained in this manner, as you see on this slide. So essentially, this is the broad architecture, right? So essentially, you take a video. Video is, of course, a sequence of frames over time. So you take each frame at a time, image frame, and you pass through image encoder. And this image encoder also makes use of some memory. So essentially, there's a memory bank. The memory bank supplies this extra memory, which is essentially what were the masks which were done on the previous frames for this object, and what were the features of the object. It supplies that memory, and then the current frame is basically looked into, is processed by in the context of that memory. By coming up with this memory attention. So which memory is important and not important and so on. So as to essentially then come up with a revised image embedding. Now this revised image embedding is basically passed through the mask decoder along with the prompt, if any, that the user has passed on this frame. Of course, the mask decoder essentially comes up with a particular mask, for example, this part in this particular image, right? And that's the output for this frame. Now, this output, of course, is also encoded the mask is encoded in a particular way so as to essentially store in the memory bank, right? So more details are as follows. So if you look at this image encoder, well, the image encoder, now remember, this is an interactive approach. So basically, at any point of time, the user may stop the video and then say, oh, there is a problem here, and then provide that prompt input. Okay, and then SAM2 runs again so as to compute the mask for all the remaining frames in the video, right? So, however, the first part, the image encoding part, is just done once. So it is done once. The image encoding is just done once for the entire interaction. And the role is to sort of figure out the unconditioned image embeddings, tokens per frame, right? In that senses. And specifically, they use a particular model called as hierarchy image encoder model. It's a hierarchical image encoder model, which can give you multi-scale features from each of those image frames. Okay. Now, the next component is this memory attention component. This component is basically transformers-based component. It has L transformer blocks, and each block basically does self-attention. After that, it does cross-attention. The cross-attention is done using these memories, so from the memory banks, okay, from the memory bank. And these memories essentially could be for prompted versus unprompted frames. So prompted frames are those where the user supplies the input, right? Unprompted frames are those where the SAM2 model basically just computed the location of the object or the boundary of the object without really user providing any input. Okay, and also uses some. It also computes this cross-attention using object pointers, which are also stored in the memory bank. So memory bank basically stores three things: object pointers, prompted and unprompted frames in the memory. Okay, we'll talk more about the memory bank on the next slide, but the idea is that that memory is basically used to for cross-attention with the image embeddings there itself. Okay, followed by MLP, of course. So essentially saying memory attention is basically transformer blocks. Which has self-attention, cross-attention with memory from the memory bank, and also MLP, feed-forward layers, basically, right? Now, when the user is applying prompt, you need some prompt encoder. The prompt encoder basically acts as specific, in different ways for a mask, which is basically a dense prompt, versus points and box, which are basically sparse prompts. So for sparse prompts like mask, like the clicks and pounding box, basically they're represented by position encodings. And you basically also add segment embeddings, where segment is defined as the prompt type here. Right? So you add prompt type encodings along with the position encodings. Okay. So however, masks basically are dense in nature. So you basically, and they are images in some way. So you basically do convolution on them, and then some with the frame embedding so as to essentially get the prompt encoding. Okay. Now you also prompt memory encoder, right? So memory encoder, what does it do? Well, it basically comes up with a vector representation for the current frame so as to store in the memory bank. And that is basically obtained by downsampling the output mask. So you take the output mask, this output mask, You downsample it and using a convolution module, and then you also sum it element-wise with the sum of these representations coming from the image encoder side. Of course, it's not shown in the image, and that is why I drew the arrow manually, right? But you basically get those image embeddings from the image encoder, and you also combine it with the mask encodings, and then you do some convolution processing so as to essentially get a vector which you could store in the memory bank. Okay. Now, this part is basically the same figure as from the previous slide. Of course, the right side figure that you see here essentially enlarges on this mask decoder. So this mask decoder, the details are on the right side, and we'll talk about those details on the slide. Okay. So, but a little bit about the memory bank. As I mentioned on the previous, while discussing the previous slide, memory bank consists of three important things. Two of them are the spatial memory. So in the sense, they basically keep memories of n recent frames and also m prompted frames. Okay, so in a queue, so you don't really keep all the frames processed so far, but only n recent and m prompted frames. You basically keep the information after the memory encoder has encoded and stored them as vectors. But you also store object pointers. And what are object pointers? So basically, you're tracking a particular object or multiple objects. And for each of those objects, you basically compute features and you store them in the memory bank also. They're high-level semantic information of the object based on the mask decoder output tokens of each of the frames, right? So that's that. Now, and as we discussed, this memory attention guy is basically going to do cross attention between image encoder embeddings and the memory bank embeddings, memory bank vectors. And it's basically going to use all of these things, spatial memory as well as the object pointers while computing this cross attention. Now, remember when you're doing these n recent frames, you basically also encode the temporal information so as to indicate, how far away this frame was from the current frame. Okay. So now what does the mask decoder guy do? So well, mask decoder guy essentially takes the image embedding. So although again, it's not shown here directly, but the mask decoder guy basically gets the image embedding, the image embedding from the memory attention module, right? It also basically gets these prompt tokens, which are basically mentioned here, these prompt tokens, and it outputs several things. Of course, the main thing is the mask itself. It also, of course, outputs object pointer, which can go into the memory. It outputs occlusion score, and we'll discuss why. But it also outputs IOU scores, so as to figure out, what is the, again, we'll talk about why it outputs the IOU scores also. Okay. But let's basically see what does this mask decoder do. So mask decoder is basically taking these prompt tokens and taking the image embedding tokens. And, on the prompt tokens, of course, it first does self-attention, then it does cross-attention. So cross-attention between the prompt tokens and the image embeddings, and then image embeddings and the prompt tokens, right? So once it does those both ways of cross-attention, two-way cross-attention in that senses, of course, it has some dense layers also, right? This output is combined, the output from both the token to image attention and image to token attention, so as to get this matrix, which is basically used to compute these three heads: object pointer, image, IOU scores, and occlusion score, right? And then on the other hand, this output is also given to upsampling layers, convolutional upsampling layers, so as to essentially get the masks, right? Mask which is of the same size as the original image frame, of course, because we are doing segmentation in that senses. Okay. Now notice that this upsampling module also takes representations from the image encoder itself. So this upsampling model also takes representations from the image encoding layer itself. Okay, that's that. Now, why do you need this IOU scores and occlusion score, right? So the important point is here. So, when you're dealing with ambiguous prompts, for example, if the user basically clicked, a positive click on a particular part of a tire, right? A tire of a bike, right? Now, the user may mean that the tire is positive, or the user may mean that the entire bike is positive, right? Now, there is ambiguity there. And the idea is to predict multiple masks in that case, and that's an ambiguity even in a single frame. But then this ambiguity could also extend to the video across multiple frames. So it could extend across multiple video frames. And then, if there's no other signal to essentially resolve this ambiguity, then this IOU score, whichever particular object essentially has a higher IOU across frames is the one that is selected. Okay. Now, unlike image segmentation, in video segmentation, a particular object may just disappear in certain frames. And that is why you also need an occlusion head here, so as to basically predict whether the object of interest is actually present in the current frame or not. Okay, so that is why you need those extra heads. Okay. Now, how is training done? Well, training is done basically for SAM2 by sampling 8 frames, sequences of 8 frames, and randomly selecting 2 frames where you would supply this interactive input. The interactive input is automatically supplied based on existing training data, rather than actually, of course, having human in the loop, right? So, this interaction is basically to provide corrective clicks or corrective masks and so on, prompts essentially for 2 frames out of a sequence of 8 frames. Okay. So, of course, the goal for this training, the objective to be maximized is to accurately predict the mask across each of those frames in the entire video, also called as the masklet, right? And therefore, you compare with the ground truth masklet so as to decide the loss. When you're processing an entire video, the interaction has to start right from the frame one. Frame one, the user has to specify what is the object of interest that they want to track, right? So initial prompt, essentially, basically on that frame one, 50% of the times they basically just use a positive click, 25% of the times they use a ground truth mask, and the remaining 25% of the times they basically use a bounding box. So that is how you essentially start the process for training. Okay. So how is this SAV dataset created? So the dataset is created in 3 phases. I'll not go into details about how these 3 phases work. But once this dataset is created, the model is trained in 2 phases. First, you pre-train the SAM2 model on static images, not videos themselves. And then second, you basically train them on the SAV plus some internal dataset to meta AI. Right? The SAV dataset is large. So essentially, if you really compare it with existing other video object segmentation datasets, SAV dataset has 50.9 videos, 51K videos, right, which is huge. Okay. Also, they have like 190.9K masklets. If you combine with the automatically generated masklets also, which they verify the quality is good or not, well, it's a huge number of masklets with about 35.5 million masks, right, across 4.2 million frames. So it's a huge, huge data set, right? And the way they created data set, of course, they created it using manual labeling also. So, they asked people to manually label using clicks or masks and so on. But then they also essentially did auto labeling. And as you see, auto labeling of different objects in a particular image can lead to so many diverse kind of objects. And also, it can lead to really huge coverage, right? If you compare this manual labeling versus automatic labeling, you see automated labeling gives you way more number of objects rather than what one can get by manual labeling. Of course, one has to verify if these objects make sense or not, and which is why they also have a verifier module in that sense while creating the data set. So these are some examples of the data set. You can see how interesting, across these 3, videos depicted using a few frames, how interesting objects have been tracked nicely in this data set. Okay. So how does SAM2 perform? Well, they basically do several experiments. In fact, they do experiments on many, many data sets. So they found that SAM2 gives you better segmentation accuracy while using 3x fewer interactions than prior approaches. Okay, this video object segmentation basically does involve human interactions, and there are other 2 methods, XMEM plus and QT, which they compare with, and they find, what they did was on 9 different data sets, they basically tried to do interactive evaluation with the maximum of 3 clicks per frame. And they found that, if you allow 8 frames, all 8 frames, the user interaction to be present, then you get a very good score. So they compute what is called as J and F metric, and you basically get like 85% score on that metric if you basically allow on all 8 frames human prompting and 3-click kind of prompting. Only clicks, no masks or no bounding boxes. And clearly you observe that SAM2 basically performs really better compared to SAM, which is an image-based segmentation model, plus XMEM, which is basically the video object segmentation in that sense, right? So, or SAM plus QT. So compared to those baselines, of course, SAM2 works better. Okay. It is 6x faster than these baselines, which is also good. It basically shows really awesome zero-shot benchmark results on 17 different video segmentation, 37 different image segmentation methods. When you compare it with the when you perform semi-supervised videos object segmentation, which basically means just on the first frame of the video, the user basically provides click, box, or mask prompts. You basically observe that on 17 data sets, SAM2 outperforms the other 2 methods really well. In various cases, when you only allow 1 click or 3 clicks or 5 clicks or bounding box segmentations or even mask-based inputs from the user. Mask-based interactions in that sense, right? They also did fairness evaluation. So does the model really detect males versus females in a scene more accurately, right? So they observed that yes, there is some bias. So essentially, when you provide one-click, three-click, or mask kind of prompting, so for males, typically the accuracy is higher, the J and F scores compared to females. Also, what is observed is that but then from an age perspective, you do observe that typically there is no such pattern. So essentially saying that the model is fairly fair, reasonably fair across different people categories as evaluated on this EgoXO 4D dataset. So in summary, in this video, I talked about the SEM2 model, segment anything model. It extends the promptable segmentation task to videos, and it equips the SEM architecture to use memory when applied to video. So memory of, what were the object masks in the previous few frames, what were the prompts provided in the previous few frames, and also what were the features of those objects, right? And then they basically also contributed a diverse SAV dataset for training and benchmarking video segmentation methods. So that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.